As I said earlier, regularization as a theory, right, is something that actually allows you to robustly estimate an unknown when there is noise, and when probably there are issues with existence, uniqueness, and so on. So in a sense, right, if you want to summarize this theory of regularization in a few sentences, right, you can effectively say the following: the theory of regularization. Okay, let me just write it down. The theory of regularization is a formal process. Process of incorporating prior knowledge. Okay, and we saw this already that throwing in as much knowledge as you have about the unknowns, right, helps in estimating them robustly. Process of incorporating prior knowledge to robustly estimate the latent unknown, the latent or the hidden or the whatever, right, the actual quantity that is of interest, the latent unknown, which in our case is the clean image in our case, clean deblurred image in our case, right? For us, for the image deblurring problem, it turns out that what we are trying to solve for is this clean deblurred image in our case. Okay, we saw for example how a deterministic kind of a regularization theory can actually be employed for this purpose. Right? We saw a constrained least square solution where we could throw in a prior. Okay, and that you see prior could be in terms of the Laplacian of the image, right? Should be as small as possible, or it could, or for example, when you could talk in terms of the L1 norm of the norm of the gradient of the image along x, gradient of the image along y, and so on. Now, right, we'll actually turn our attention to stochastic ways of actually solving these kind of ill-posed problems, and of course, it is specifically for us the image deblurring problem. We'd like to see how to solve them using a stochastic framework, using what I would say, a stochastic regularization route. And right, and we will see that the same kind of things, right, which we had earlier when we did a deterministic regularization, in the sense that, right, the same kind of things that we had, like smoothness prior and so on, right, or whatever, right, when priors, okay, which we could employ there, we will show that, right, there is a parallel, right, even here when we adopt a stochastic regularization route. Moreover, one specific filter, what's called the Wiener filter, right, which we are going to see for image deblurring, which is a popular filter. We will see that it is a filter that incorporates this regularization notion in an implicit manner. While of course you could have stochastic estimators that could also do it in an explicit manner, something like let's say a map estimator. Okay, but then in this course it will limit ourselves to the Wiener filter, and we will see how this regularization theory that we've seen earlier. But then when you adopt a stochastic route, for example, when you arrive at a Wiener filter, we'll be able to see as to how the prior comes in and how it helps to regularize your solution and so on. Okay, so the idea is to embark on stochastic estimators, right? So from now on, instead of talking about least squares, right, we'll talk about mean square. Okay, so instead of saying least square error, okay, until now, okay, whenever we did a deterministic kind of approach, right, it was always about like least squares error. Now we'll talk about a mean square error. Okay, so we'll talk about mean square estimation. We'll talk about estimators that are constrained to be linear. We'll talk about estimators, right, that can be nonlinear in nature, and so on. Okay, and when a nonlinear estimator can also turn out to be linear, and what conditions, and so on, and how all of this leads you to the Wiener filter. Okay, that is the idea. So let me write this as stochastic regularization. Okay, this is yet another approach to solving ill-posed problems. problems. Specifically for us, deep learning problem, they made deep learning problem and revolves around the notion of mean square error. Of mean square error, right? As opposed to least square error, right? Which we had seen earlier, mean square error. MSE, right? As it is called. Let's first look at what do we mean by, say, mean square estimation. Mean square estimation, right? What do we exactly mean by that? Okay. Suppose we start by saying that we would like to do mean square estimation, which I'm going to write as MS. Mean square estimation. Suppose I'm interested in doing mean square estimation. Suppose I'm interested in doing mean square estimation of a random variable y. Okay, that means we are interested in an estimator as a random variable y, but suppose by a constant c, right? This may not be the most obvious thing that you would want to do, but let's say, right, we start with the simplest of cases, which is to say that I want to make an estimate of the random variable y by a constant c. So the mean square error, right, is in fact given by expectation. Because now we are dealing with random quantities. Y is random, although c is a constant. Expectation y minus c square. That means, right, we would like to find a c such that this expectation y minus c square is as small as possible. So suppose the error, right, we indicated as e, then it is e is equal to y minus c the square, which in turn is y minus c the whole square fy of y dy. Okay, and for e to be minimum with respect to c, okay, which is a constant in our case, with respect to c, let's do dou e by dou c. It will be equal to, or we can whatever, d by dc if you wish, will be equal to 2 times y minus c fy of y dy. Well, you can put minus 2, okay, just to absorb the sign. This should be equal to 0, okay, which in turn means that integrals of the y minus 2, right, can just be thrown away, and then we'll have y minus c fy of y dy, right, is equal to 0. And this comes from here, okay, because this minus 2 goes away. Or in other words, we'll have integral y fy of y dy is equal to integral c into fy of y dy. However, because c is a constant, right, we can pull c out and we get integral fy of y dy, but this is 1, right, because this is simply the area under a PDF. Therefore, this is equal to c. Therefore, we get c to be equal to integral y into fy of y dy, which is but the expectation of y. So it actually amounts to saying that in the absence of any other information, right, if I had to make a best mean square, right, a minimum mean square estimator for y, in the absence of any other information, when I don't observe anything about y, there is nothing else that I know, then the best estimate that I can make is the best minimum mean square error estimate that I can make of y is simply the mean of y, right, the mean value of y, expectation of y. Of course, right, it is not really that very interesting because you would not typically want to do that. What you would instead want to do is the second situation. The second situation wherein, let us say that we ask for a nonlinear mean square estimator. Here, of course, this estimator was simply a constant. Now, let's look at nonlinear mean square estimation. We call it nonlinear because it turns out that the estimator is generally nonlinear. Okay, so here, right, so what we're going to do is estimate. So the kind of problem statement changes is estimate y not by a constant, okay, not by a constant, but by a function, let us say c of x of another random variable, let's say of the random variable x, assuming x carries information about y, right? Because the whole idea is that we are not able to observe y directly, but then through x, right, which is another random variable, And suppose right, x were to carry information about y, right, then we would like to now find out the optimum C of x such that expectation y minus C of x squared is as small as possible. Assuming x carries, right, carries information about y. Okay, so suppose we know that x carries information about y, okay, then we would like to find a C of x which is optimal. So we can call our error now, we can redefine the error as expectation y minus C of x, where x is also a random variable now, C minus x square. Okay, now such that, so find C of x such that E is minimum. Okay, or in other words, right, what you're sort of saying is that expectation y minus C of x square should be less than or equal to expectation y minus some g, right, any g of x square for any g of x, linear or non-linear. Okay, it's what you're asking. Right, that means the variance, right, that you have here, okay, that you compute using C of x should be such that right, this variance is less than or equal to, right, any other function of x which you might want to take, linear or not. Okay. Now again, right, let's first expand this e. Okay, so we have e to be equal to integral expectation. Let's first look at this as c minus x the whole square, which we know is integral y minus C of x the whole square. And now we need a join PDF because of the fact that both x and y are random variables. Okay, let's put a double integral dx dy. And this furthermore, right, we can split this as double integral y minus C of x the whole square. And this, let's just write this down as f of y given x, fx of x dx dy. This can further be written as integral fx of x, right? Let's just pull this fx of x out from the second integral. Then inside we'll continue to have y minus cx the whole square, and then fy given x, dy, and then dx outside, right? Because this entire thing is of course a function of x. Now, since fx of x is always greater than or equal to 0, e is minimum. E will be a minimum provided the term inside provided equivalently, right? It means, right, provided e bar, let's denote this as e bar, which is integral y minus c of x square fy given x dy is minimum. Or in other words, right, we can look at dE bar by dCx. So I've changed e to e bar. Okay, so dC of x, right, if you do, then you get integral. Anyway, all these integrals are typically from minus infinity to infinity unless stated otherwise. So this will mean you will have 2y minus c of x, okay, minus 2 maybe, and then fy given x dy. Okay, this whole thing is equal to 0. So in order to find the optimum x, right, we have to equate this to 0. Or in other words, we will have integral y fy given x dy is equal to integral c of x fy given x dy. This is equal to c of x. Or in other words, c of x, okay, as you can see, is integral y given x dy, or this is also called the conditional mean of y given x. Okay, this is the conditional mean or conditional expectation or conditional mean as it is called, mean of y given x. Okay, now the point is, right, this quantity, okay, this conditional mean, the conditional mean is typically the CM, okay, let's call the conditional mean, is usually a nonlinear function in y, in x, nonlinear function in a function of x, and which is why we call this a nonlinear mean square estimation, right? Estimator. Now, C of x is now and it's the estimator of y, and if you substitute the value of x in this nonlinear function, right, then I mean you would get an estimate of y for that particular value of x. So C of x is an estimator. It's a random estimator, right? And for a specific choice of x, you would get a specific value for y. Now the conditional mean has a very, very interesting property, what is called the law of iterated expectation. Okay, there is something called the law of iterated expectation. Okay, this is an important property of the conditional mean, and what that amounts to saying is that expectation of y given x is equal to expectation y. Okay, we can show this. Okay, now the main thing that you should kind of bear in mind is that there are two expectations here. Remember that the outer expectation is with respect to x, the inner expectation is with respect to the conditional mean of y. Okay, so you should actually keep that in mind when you write down the integrals. So suppose we start from the left. We start from the left by looking at expectation y given x. Okay. So suppose we call this some phi of x, right? Suppose we call this as some phi x. Then we know that this is integral phi x fx of x dx, right? Since this outer guy is with respect to x. And this further is equal to, now if you substitute for phi of x, which is nothing but the conditional mean of y given x, it is fy given x dy, okay, dy. And then you have fx of x dx. Okay, or this in turn becomes integral y. Now, if you were to combine, right, these two, okay, let's again rewrite this. Fy given x fx of x dx dy, and these two will give you the joint PDF y fx y xy dx dy. Okay, and this can further be simplified to get the marginal by integrating this joint PDF. So we can write this as integral. Okay, we can write this y, and then we can integrate fxy with respect to dx and the whole thing dy. And this in turn will give you integral y, and we'll be left with fy of y. Okay, after you integrate x out, you get fy of y dy, that is equal to expectation of y. Okay, or in other words, right, if you were to look at it, okay, this is called the law of iterated expectation. Okay, because it's like an expectation over an expectation. The other way to kind of look at it is the conditional expectation is an unbiased estimator. Right, like I said, earlier when we did image sequence filtering, right, at the time we had actually talked about this point that if the unknown quantity that you're trying to estimate itself is random, then when you have an estimator that is trying to estimate that, the estimator is unbiased if the mean of the estimator is equal to the mean of the unknown, right, that you're trying to estimate. In this case, the unknown is y, which is random, and therefore, right, another way to look at it is estimator is y phi of x. Therefore, the mean of phi of x is equal to the mean of x, mean of y. Therefore, you can also, this also leads to the conclusion that what you have is an unbiased estimator. Okay, another way to right, interpret this result. Now, moving forward, let's also, okay, and this can also generalize, right, to the case when instead of one random variable x, suppose we have several of them, and we are still trying to estimate a scalar random variable y, then if y is to estimated, then this generalizes, this conditional mean result generalizes in the following way. If y is to be estimated, from x1, from random variables x1, x2 all the way up to xn, then the minimum mean square error estimator, right? Minimum mean square error estimator, which is the conditional mean, of course, which is the conditional mean. Conditional mean is given by, you can write this as some y hat, which is conditional mean of y given x1, x2 all the way up to xn, or you can write this as expectation y given a random vector x, right, where this random vector encompasses x1 to xn, okay, where you can say x equal to x1, x2 all the way up to xn, all random variables. Now, till now, right, I've been saying that that the conditional mean is in general a nonlinear function of x. Okay, in this case, it will be a nonlinear function of x1 to xn, right? If it basically depends upon multiple random variables, then right, it will be a nonlinear function of x1 to xn. Now, it turns out that you could have a very, very interesting case wherein the conditional mean becomes linear, right? In the sense that in general, a linear estimator would be suboptimal, whereas a nonlinear estimator, which is the conditional mean, right, minimum mean square estimator, which is the conditional mean, is optimal, right? However, if you constrain an estimator to be linear, then it is expected to be suboptimal. But then you can show that situations can arise when under certain conditions on y and x, right, that y and x should satisfy, then it can turn out that a conditional mean, right, can turn out to be a linear function of x. In which case, a linear estimator is also the best, let's say, MMS, right? It's not suboptimal anymore. But in general, one should remember that the conditional mean is nonlinear in x. Now, let's first let us kind of look at linear mean square estimation, linear MS estimation. Now, as it of course, right, clearly indicates, right, a linear mean square estimation. So a linear mean square estimation, right, on most occasions, so let's write this down. On most occasions, one is willing to settle down or accept for a linear estimator, because as we know, a linear estimator is something that kind of gives you a better handle, even though it may be suboptimal, but then it is something that we can understand, that we can analyze, right, theoretically analyze and so on. Nonlinear estimators can be really very, very tricky to analyze. For a linear estimator, although it will be suboptimal. Although it can be suboptimal, or it will typically be suboptimal. Okay, that's what we mean. Sometimes in some special cases, it can be the optimal estimator. Okay, and we would like to see, right, examine how to actually arrive at a linear mean square error estimate.